Case Western Reserve University's Institute for the Science of Origins proudly presents the Origin Science Scholars Program. The Institute advances the scientific understanding and application of origins and evolution of human and natural systems. The Origin Science Scholars Lectures are presented with the assistance of Case Western Reserve University's Siegel Lifelong Learning Program, College of Arts and Sciences, and Media Vision. Tonight's speaker is Dr. Leslie Wade, who is Assistant Professor in the Department of Physics at Kenyon College. Dr. Wade earned his PhD in 2015 from the University of Wisconsin-Milwaukee, having joined the LIGO Scientific Collaboration in 2010 as a graduate student. His work includes gravitational wave physics, astrophysics, and computational physics. Please join me in welcoming Dr. Wade.
Thank you, and I am very excited to talk with you about when black holes collide. Okay, and I'm going to be doing this on behalf of the LIGO Scientific Collaboration, which is a group of 1,000 or so scientists who all work together to do this great work that I'm going to talk about. Okay, so in February, this was the scene.
Ladies and gentlemen, we have detected gravitational waves. We did it.
So this was really, really exciting for us. We had known about this event for some time. It actually happened in September, and we announced it in February. So the excitement had been building for a while, and I want to tell you all about it. But first, I need to tell you about black holes, and I need to remind you about my wife's talk last week about what gravitational waves are. All right? And then I want to tell you a little bit about how we search for gravitational waves, and then how we extract information from gravitational waves that we found. And once I've done those two things, then I can finally get to telling you, well, what did we find, and what have we learned? Okay, so I'm starting with background here. So the first question is, well, what are black holes? All right, so imagine I'm in Cleveland, which shouldn't be very hard to imagine. And imagine I'm throwing a baseball straight up into the air. I asked my student about how fast I could throw it. He said 70 miles per hour. I'm not sure I could do that, but let's just give me the benefit of the doubt. I throw it straight up. What happens? It falls right back down, right? Goes a little bit, but falls right back down. Now imagine we had a Cleveland Indians baseball player. I think it's Corey Kluber that I checked his fastball is about 93 miles per hour, at least in game one when I looked it up. What happens when he throws the ball straight up? Makes it further, but it falls back down. Alas, gravity. This begs the question, or at least for scientists, it begs the question, well, how fast do I have to throw the ball straight up in order for the ball to escape that gravitational pull of Earth? And I've done the math for you. It's about 25,000 miles per hour, or maybe something more understandable is 7 miles per second. If I could just throw it that fast, I could escape, or the ball could escape Earth's gravitational pull. What we call this is escape velocity. Okay? Every massive object has an escape velocity. What velocity do you need to throw the ball in order to escape the gravitational effects of that mass? This is the only equation in my talk, but it's the equation for escape velocity. It depends on mostly two things. The g there is a constant. It's the gravitational constant. It shows up in all of our gravitation equations. But the other two terms here are mass and radius. So the escape velocity really only depends on the mass and the radius of the object. Okay, so if we had Earth here, and we wanted to increase the escape velocity, all we have to do is inject it with mass, right? You make it more massive, keep the radius the same, just inject more mass into the system, the escape velocity increases. The ball won't travel as far at a given velocity, right? You have to throw it faster and faster in order to escape the Earth's gravitational pull. And if we inject enough mass, we can increase the escape velocity to be greater than or equal to the speed of light, which is the cosmic speed limit. Nothing can go faster than the speed of light. And when we do that, not even light itself can escape the gravitational pull of that object, and we call that a black hole. It takes about 2,000 suns worth of mass injected into Earth to create a black hole at that radius. Another way you could create this black hole is instead of adjusting mass, you adjust the radius. So you take the Earth and you just squish it down. And how big do you think it would have to be in order to be a black hole? A pea? Yeah, it's pretty close. About 9 millimeters, which is a little bit bigger than a marble. If we take all of the mass of Earth and shove it into a marble, we'll have a black hole. And if we stand on the surface of that marble and throw a baseball at the speed of light, it won't ever escape. So the idea here, oh, am I off? Okay. The idea here is that black holes are formed when enough mass is gathered into a small enough space, right? And gravity doesn't just act on massive objects, it also acts on light, which I'm about to tell you in a second, okay? And so you get a black hole when you've shoved enough mass into a small enough space such that the light is not even fast enough to escape the gravitational pull of that object. That's what a black hole is. Okay, so switching gears a little bit. What are gravitational waves? Well, you learned this a little bit last time from Maddie, but if you weren't here, I'm going to tell you a little bit about it. And before I can even mention gravitational waves, I have to tell you about this theory of gravity called general relativity. So the original theory of gravity was that masses pull on each other through some force. This is called the Newtonian theory of gravity because Newton came up with it. And planets are in orbit because of this force. Okay? But there were some problems with this theory of gravity. Most notably, and maybe most fundamentally, is that it violated the cosmic speed limit, that nothing can travel faster than the speed of light, not even information about masses moving. Okay? So Einstein came along and just completely reimagined gravity. And I'm just going to skip into exactly how he imagined gravity instead of telling you how the steps that led him to reimagine it this way. So gravity in Einstein's theory is the following. So it turns out that both space and time are connected. They're not different things, and we call this space-time. And space-time can actually be curved. What happens when you curve space-time is that things traveling through space-time take different paths than if it weren't curved. And Einstein theorized that, well, massive objects curve space-time. And when massive objects curve space-time, other objects traveling through that curved space-time take different trajectories, different paths. And he's able to explain all of the orbits and all of the gravitational effects that we see, or as we've always thought about being forces. He's able to explain them as just a consequence of the geometry of space-time. So what's being shown here is a way to visualize this idea. So space-time is 4 dimensions, 3 spatial dimensions, 1 time dimension. And then since we can't visualize 4 dimensions being curved into a 5th dimension, we're going to simplify things. We're just going to consider 2 dimensions like this sheet, and then we're going to curve it into a 3rd dimension so we can visualize what's happening here. The idea is that the mass of the sun and the mass of the Earth both curve space-time. The mass curves it more, the Earth curves it less. And then the Earth, while traveling in this curved space-time, is actually going to orbit the sun. If you've ever been to a science museum and seen those black funnels that you can roll a coin down, you've seen this happen before. The coin is just traveling actually on the straightest possible path and orbiting that thing that's curving the space-time. Okay, so the main idea here is that gravity is not a force. It's just a consequence of the geometry of space-time. So when you start curving space-time, what happens when you take those things that curve space-time and move them around? Most notably, what we have found via gravitational waves, which I'll get to in a second, are 2 bodies orbiting each other, 2 really massive bodies, 2 bodies that have extreme curvature of space-time orbiting each other. what will happen is that there will be ripples in this space-time fabric that propagate away from the source. And these ripples in space-time are what we call gravitational waves. So the next question, how do we detect gravitational waves? Well, first we have to know what gravitational waves do. So what is a stretching of space-time, or this curvature of space-time, which is a stretching of space-time? What does that mean? Well, imagine that we had a bunch of particles just kind of floating around in outer space, so there's no other forces on them. And then imagine that a gravitational wave were going through the center of the screen. What would happen? Well, the gravitational wave is a stretching or compressing of space-time itself. So what happens is that the distances between particles will increase one way and compress, so decrease the other way, and then compress one way and increase the other way. This is a single polarization of gravitational waves. There's an orthogonal polarization. It just means another polarization that all gravitational waves are made of. But this is the general idea, is that distance changes. And if we could just measure the distance, then we could detect gravitational waves. But you can't really just measure the distance the way we normally think about measuring distance with our tape measure or our meter stick, because the gravitational waves also change the lengths of those things. So what do? Well, we go to the physicist's favorite toy, our duct tape, if you will, the laser. We use it for everything. We're going to use it to measure length, too. Okay? This is a picture of a Michelson Interferometer. In the bottom left is a laser, in the middle is a beam splitter, and then those two in the upper corners are mirrors. What happens is the laser will be split by the beam splitter, reflect off the mirrors, and recombine. And where it recombines, there's interference that happens because light is a wave. So it's going to break it down for you a little bit here. So light is a wave. It splits on the beam splitter, gets reflected back by the mirrors, and when it recombines right here, we set it up to combine out of phase. When things combine in phase, they constructively interfere and you get more light. When things combine out of phase, they destructively interfere and you get no light. And then when the distances between the mirrors and the beam splitter change, you get more light or less light. And that is how we're going to detect gravitational waves. The LIGO collaboration has built two really big interferometers. One is in Hanford, Washington, in the upper left. I visited that one a few times. And the bottom right is in Livingston, Louisiana. Unfortunately, I haven't made it there yet. LIGO stands for Laser Interferometer Gravitational Wave Observatory because we use laser interferometry to observe gravitational waves. Okay, and that's the idea. These are about 2.5 miles long in their arms. And even then, I showed you a very simplistic version of the instrument. But instead of just reflecting and recombining, they actually reflect, and then we bounce them back those 2.5-mile arms many times before they recombine, making the effective length of the arm even greater. So these are extremely impressive machines. And there's been a lot of engineering going into building these machines, and in fact, they are the most precise instruments in the world. All right, and before I get to the questions, I just want to tell you about some other instruments. I'm talking only about LIGO for the rest of the talk, but I also want to give some credit to some other gravitational wave interferometers that are either coming online or are online already. So there's one called Virgo, which is in Europe. This is a gravitational wave detector that will be the first of these series of other detectors to come online and start observing with the LIGO detectors. And then there's one in Germany. There's one, the Germany one is always on, but it's a lot less sensitive. But we use it for prototyping. And then there's going to be one coming up in India, which is actually going to be part of the LIGO collaboration, and then another in Japan.
Okay, you talked about extending the length of the arm, thousands of miles by bouncing the light back and forth, back and forth, back and forth. How does the light eventually get out? It seems to me like it would just bounce back and forth forever.
That's a really good question. So the way that we do it is through a device called a Fabry-Perot cavity. So you have a partially transmitting mirror, call it, which the light can go through one side, and then it has a % chance of bouncing back, a very high % chance, but some of the time it will go through. So on average, it takes like, let's say like 99 times of bouncing back and forth before one photon will go through. So we actually build up power with this device, and because it's just a probabilistic effect, you don't have to worry about orienting the lasers exactly right in order to get them to bounce back and forth enough times and then still recombine exactly right.
Who funds all this?
The NSF, the National Science Foundation. Nobody else for LIGO. The others are funded through other programs, but the LIGO is pure NSF, which was actually a big deal because LIGO was a very controversial thing to put money into. Nobody knew if it was possible to detect gravitational waves. Einstein thought it wasn't possible, or at least wouldn't happen, maybe even in the human lifetime, right, to detect gravitational waves. And the first iteration of LIGO didn't detect any gravitational waves. So they put tons of money into this thing, and we said, okay, we're going to detect gravitational waves, and it didn't happen. Or at least we hope to detect gravitational waves. I think honest estimates showed that there's a very good chance we wouldn't, and it was more of a prototyping thing. But after not detecting gravitational waves, NSS still gave us enough money to advance the instruments to the capabilities that we thought for pretty much for sure that we'd find them. And they put a lot of trust in the LIGO collaboration, and apparently it paid off. So.
You showed us an animation of spiraling objects emitting gravitational waves. Can you comment on the nature of the gravitational waves that may emerge from an object traveling in a straight line?
Yeah, so I'm going to say a little bit more about that coming up, but essentially we know what they should look like. So if you take general relativity, which is our theory for gravity, you can input certain things like, okay, I'm going to input two masses that are in orbit, and then general relativity will tell you what the output is, what the gravitational wave should look like. So I'm going to show you some models of what we expect to see in coming up. But essentially, it's that they orbit, they lose energy to gravitational waves, which tightens their orbit, which actually speeds them up. So they orbit slowly, they get faster and faster and faster. They're losing energy to gravitational waves, which causes them to inspiral, but the inspiraling actually speeds them up, and then they eventually collide and merge.
Could you tell us whether the wavelength is fixed? What fixes the wavelength, and does it change as it propagates out? Yeah,
so the wavelength does change. So what sets the wavelength, wavelength is related to both frequency and the speed at which it travels. Okay, so the speed is fixed, but the frequency changes. So when they start off very far from each other, the frequency at which they orbit is very small, and then when they come together, they start orbiting faster and faster and faster, and then the frequency increases. So the wavelength does the opposite.
I'm just curious to know, once you've found and I guess looked at in some way gravitational waves, what have you got? Is this a tool for exploration of our universe or for exploration of our history from the Big Bang? What have we got?
We've got a telescope. So it'll work exactly like other telescopes work. We will find things out in space. You're right that it actually tells us about the history, in that the things that we see happened a long time ago because they were really far away, and it takes gravitational waves a certain amount of time to go from that event to us. Gravitational waves travel at the speed of light, so if we know the distance, we can actually get how far back into the universe we're looking. Now, there are not... Tom Giblin, who will speak next time, might tell you a little bit more about what LIGO can tell you about the history of the universe. My understanding is it's not going to be able to tell us very much about the history of the universe, although it has some potential. It's more going to be astrophysical. So binary black holes or neutron stars or maybe supernova events, we'll be able to see all these things and learn about the different mechanisms creating those things. I'm not so sure what it can tell us about cosmology, which is the study of the history of the universe. But Tom might be able to tell you more because he's looked into this more. He's actually a cosmologist.
Thank you for joining us. You've been watching Dr. Leslie Wade telling us about black holes and how pairs of merging black holes produce ripples in space and time called gravitational waves. For more information on the Origins Science Scholars Program, please visit the Institute's website at origins.case.edu. In the next part of the talk, Dr. Wade will tell us how gravitational waves can be detected. Now, back to the talk.
Okay, so now we're entering part 2 of the talk. So how do we search for gravitational waves, and how can we learn from them? All right, so this is really my expertise. I spend all of my time building software to search for gravitational waves and building software to extract information from gravitational waves, like where were they located, or what were their masses, or were they spinning, were the objects deformed before they merged, things like that. So I want to tell you a little bit about the methodology behind how these things get done. Okay, and specifically I'm going to talk about these binary systems, so 2 objects orbiting, and I'm not going to talk about any of the other sources. Okay, so these are the ones that I focus on. They're considered to be the most promising, and indeed they're the only ones we found in the first observing run. Okay, so the first question is, well, what are we looking for? And as I mentioned before, this comes from Einstein's theory of general relativity. If you put certain inputs, like you have 2 masses in an orbit around each other, and you solve for the gravitational waves that come out of a system like that, what you get is something like this. On the vertical axis here, you have gravitational wave strength. So the taller it is, the stronger, the bigger the amplitude, the stronger the gravitational wave. And then on the horizontal axis, you have time. So the story that this plot tells is that you have 2 objects in orbit. They have notice that the crests are kind of spread out, whereas they smush together more to the right. So you have an object that's, these objects are rotating around each other, orbiting each other at a small frequency, and then they start to lose, they emit these gravitational waves which carry energy, which I told you tightens their orbit, and as their orbit tightens, they actually speed up. Okay? And then the frequency increases over here. Meanwhile, the amplitude is also increasing. All right, so what you get is an effect like this. They start out slow, they go, and they merge. And what was that weird sound that I did? Well, what we like to do is turn this wave, take this wave, which is gravitational wave amplitude versus time, and change the y-axis to be sound amplitude versus time. So we turn this into a sound wave. And why the wave sounded like that is because over there, early times, we started at a low frequency, which is a low pitch. And then we get into high frequencies as they get closer, which is a high pitch. Meanwhile, the amplitude starts off small and increases. So we go from something soft to something much louder, right? And together, that sounds like this. And when they merge, they're all deformed, but they quickly become spherical and then stop emitting gravitational waves, and that's why this dies off so quickly. We call that first part the in-spiral, where they hit the merger, and then the last part the ring down. If you change the parameters of the system, you look at small things, smaller things, it takes them much longer to merge, and they merge at much higher frequencies. If you have big things, like really massive black holes, they'll only have a a handful of cycles go whoop, 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 woof, merge at a much lower frequency very quickly. Bottom line is the shape of the gravitational wave is determined by the parameters of the source. Okay, so what does that have to do with searches? Well, in a search, what we do is we construct a bank of model waveforms. So we want to look for everything that we could see. We could see binary neutron stars, so two neutron stars merging. They have small masses relative to black holes. We can look for binary black holes, the big things, and we can look for a neutron star and a black hole. Those would be the things that are detectable by LIGO. So we construct a bank of all of these different models with different parameters plugged in because we want to search for all sorts of things. We call this a template bank. And then each template is filtered through the data looking for things in the data that match. This is called a matched filter search. And I want to give you a visualization of what this looks like. All right, so in blue, we have just kind of random noise. In red, we have a possible gravitational wave signal. So if this signal ended up in our noise, this was what it would look like. All right, so we take that data, and then we take one of our models, what we're looking for, and then we filter them across each other. And what it looks like is this. You multiply all of the points together, you add them up, and because there's, with just random noise, there's just as many points above 0 as below 0, you kind of get this effect that they all cancel out and you get something small in this axis, which I'm calling signal power. But where the signal lines up with the actual signal the model lines up with the actual signal in the data, you get a maximum in this statistic that I'm calling signal power. Another name for it is signal to noise ratio. All right, and what we do then is we apply a threshold and we say, okay, anything above this threshold might be a gravitational wave. So here we'd say, okay, here's the maximum power. This is possibly a gravitational wave. The only problem with this statistic is that peculiar types of noise we call glitches, like one point that's just very far from 0, can actually mimic signal power. So it can fool our detection statistic. So what this would look like is, you're filtering through, you get mostly 0, and then all of a sudden, bam, and our statistic is fooled. Right? Your maximum comes here, and if I were to look at the max power, it's above my threshold, and my statistic is going to tell me, hey, this could be a gravitational wave. So we have to come up with another statistic to make sure that this never happens. The other statistic asks, is the shape right? So the first one asks, is there enough power? The next one asks, is the shape right? So if there were no noise, if our detector was just perfectly noiseless, isolated from all noise, and there was a gravitational wave that hit, it would look like this blue signal. And if I filtered my model across no noise and just signal, what I get in my signal power plot is something that looks like this, where you can see where they exactly match. You get the peak, and then it kind of winds down at the end. This signal power looks a lot more like the first one, which had a signal in it, than like the last one, which was caused by a glitch. So our other statistic measures how similar are these shapes. And if they're similar, then it could be a signal, and if they're not, then it's likely just noise. So these are the two statistics that go into searching for gravitational waves, and this is how it's done. And then once we have a gravitational wave which passes both of those statistic tests, then we put a number on how likely it is to be noise or it is to be astrophysical. And then if it passes our threshold for that, we say, we announce it to the science community and to the world. Okay, so I've talked about how we find signals. Well, once we have found a signal, how do we figure out what it was? Was it black holes? Was it neutron stars? Was it something different? This is called parameter estimation. So how do we go from this, our binary system, which emits gravitational waves, hits our detector and is found by our search, and then this chunk of data certainly has a signal in it. How do we go from that to this, which is what would be quoted in an article? The mass of this system was 1.35, and then we give our uncertainty on it. Well, that last quantity is actually really a probability distribution. So the mass has a range of possible values it could take on, and the probability is highest at the roughly 1.35 range, and typically it's 90% confidence regions. That's contained within the plus or minus 0.01. So how do we go from this upper left binary system where we detect the gravitational waves to this bottom right, which is what we report in articles? Okay. Well, here we assume we have a signal. So it's past our detection statistic thresholds. And you pass it to another team, which is the parameter estimation team. We have a signal. So this is both noise. Our data is both noise and signal. Well, what do? Well, we take our data, and we take our gravitational wave model, and we guess what the parameters are. And then we subtract that guess from the data and see what we have left. So if we subtract a model with certain parameters, and you get some, in the bottom right-hand corner, you get some kind of structure here. This doesn't look like uniform noise. That means you probably haven't subtracted out the right signal. But if you subtract out, if you look at the bottom left, if you subtract out a model that has the correct parameters, what you should see is just normally distributed noise, like in the bottom left. Okay, so basically we just take guesses over and over. But we're a little bit smarter than that, okay? Instead of just taking random guesses, we have algorithms designed to explore the parameter space, taking guesses efficiently. So what I'm plotting here is two parameters of my signal. It doesn't matter what they are. And the dots are all of our guesses. This is a simulation, so I actually know the right answer. The red star, is what the true parameters are. And you can see that all of these dots are clustered near the star, near the true parameters. Well, this tells us that our algorithm is working. It's supposed to take guesses that find their way to the true parameters. This is called a Markov chain Monte Carlo. And what we do then is it actually maps out, all of the guesses map out the parameter, the probability space. And then we're able to say, okay, well, that's an area of high probability. And then we circle the 90% probability intervals. There's 90% of the probability it's within that black region, and then we can quote ranges of uncertainty on our parameters. Okay, and this is a quick simulation of what that looks like. Okay, there's mass 1 and mass 2, and you can see that they find their way over to the true value. So they start off sampling in really weird spaces, and then eventually find their way towards the true value and stick there. Okay? We have ways of testing whether we found a local maximum or a true maximum and things like that, but the general idea is that we keep on guessing very efficiently and find our way towards the true underlying distribution. Gravitational waves, though, they have a lot of parameters. I've only showed you 2 parameters so far. Indeed, there's many parameters in a signal, right? It's not just 2. For instance, with a binary system like this that might be spinning, well, there's distance. How far away is it? There's where is it in the sky? That takes 2 parameters, longitude and latitude, right? Then there's, well, how's it oriented in the sky? There's another 2 parameters. I'm up to, I'm up to 5 parameters now. There's mass 1, there's mass 2. There's time of arrival. There's what we call phase of arrival. I'm up to 9 parameters now. This is a 9-dimensional parameter space that I'm guessing through. If I add spins of each of the components, that's 3 parameters each. That's another 6 parameters. I'm up to 15 parameters. So we take a lot of time and energy in figuring out how to explore the 15-plus dimensional parameter space efficiently enough that our supercomputers can actually finish that search before I die. And that's how parameter estimation works. Okay, heavy stuff. We get to the fun stuff next. Any questions?
because I'm a beginner, I'd like to go back to the beginning. It took scientists a long time to detect the gravitational waves. What was it that convinced you, despite the fact that you had such difficulty finding them, that they were there? Was it mathematical or observation?
A little bit of both, and I'm actually going to hit that in the next part. Essentially, the idea is both, like I said. So the gravitational waves that we saw were actually, the first one was very loud. It was very different from the noise. It happened at roughly the same time in two detectors, right? So noise can be, you have two detectors across the country experiencing the exact same effect within a light travel time of each other.
What made scientists think that there were gravitational waves out
Oh, that there were. Okay.
Yes, yes.
Yeah. So first off, Einstein's theory of general relativity accurately described like everything that we had seen. And what falls out of his theory are gravitational waves. So this theory that describes everything, that it wasn't really designed to describe a lot of these things, but it did. Why would we think that gravitational waves wouldn't exist, even though they're part of his theory? That's one thing, so that's the mathematical aspect. The other aspect is that we kind of observed them indirectly already. So there are these binary neutron star systems. We can see neutron stars through other means besides gravitational waves, like radio. They'll emit radio waves from their poles. These are called pulsars. We see them blinking in radio. And we have seen them in binary systems, meaning that they're orbiting. And we have tracked their period over many years, and we find that they lose energy in just the way that Einstein would predict they lose energy via gravitational wave emission. So math and observation.
Is anybody looking at how long it takes a gravity wave to go from India to Hanford through the Earth to see if gravity travels at a different velocity through the materials inside Earth's atmosphere?
Yeah, so we can get the differences in times of arrival. There's a little bit of fudge factor because there's always noise, and it's impossible to completely distinguish it from the background noise. But all of these, everything that we've seen so far is consistent with them traveling, as the theory says, at the speed of light. They don't interact with much. They don't change speeds the way that the other types of things do as they're traveling through the different materials. They travel at the speed of light.
With the equipment that you currently have, this song from the beginning of propagation to merger is approximately, what's the range of time?
It depends on the source. So I'm going to show you two black hole systems. And it really, you could be asking two different questions. So how long did LIGO see it for? So was it in the sensitive frequency range that we can see it? That question is answerable. So for the big black hole systems that I'm about to tell you about fractions of seconds, so like 0.2, I think it's about 0.2 seconds for the biggest system. For smaller masses, it was about 1 second. And then if you go to the neutron star range, you can get even longer than that. But if you're asking a different question, which is, well, how long were they in orbit? Okay, that's not, okay. Yeah, then in the LIGO sensitive range, it ranges from fractions of seconds to, it could even be with really small things, minutes.
Our sun, we're rotating around the sun. Now you have binary systems rotating only two things. A whole bunch of planets are rotating around our sun. Our sun obviously must be rotating around something else. How do we isolate the two things?
Just to be very precise, we're all rotating about the center of mass. So like if you look at the sun and the Earth, it's not that we're rotating around the sun and the sun is staying still. It's that we're actually both rotating around the center of mass of both the sun and the Earth, which just because the sun is so much more massive happens to be pretty close to the center of the sun, right? And then I think the other question was, or the other point was that, well, the solar system is also rotating around other things, like maybe in the spiral arms of the galaxy, right? So how do you track all of this stuff?
We hope you've been enjoying the Origin Science Scholars Program with Dr. Leslie Wade. Dr. Wade is a member of the Laser Interferometer Gravitational Wave Observatory collaboration that was the first to directly detect gravitational waves. In the second part of our talk, we learned about the Laser Interferometer Gravitational Wave Observatory. In our final segment, Dr. Wade will discuss the first ever detection of gravitational waves by LIGO. Now, back to our talk.
So now I've given the background. I've talked about what black holes are, what gravity is in general relativity, and what are gravitational waves. And then I told you through the data analysis perspective, how do we search for them and what can we learn from them. And now I get to do the fun thing, which is tell you what we found so far and tell you what we have learned from the things that we've seen. Okay, so a long time ago in a galaxy far, far away, this happened. So this is actually the astronomy picture of the day. On the day that we announced the discovery of the first gravitational wave detection, we're really creative. We call it GW, gravitational wave, 2015, 09, September 14th, 2015, we saw a gravitational wave. Okay. The blue and the red are the signals that we saw in our detector. With only very slight modifications to the data, we were able to make something that looks like this, which you can kind of pick out the signal by eye. Right? So it's kind of at the middle of the screen, you see some periodic motion which jets above any background noise in our instrument. And then you can see that periodicness increase in amplitude and increase in frequency as well. These peaks get closer together. This is exactly how I described an inspiraling object, or an inspiraling system, right? And then they die off. Okay? So this is what we saw in our data. We never expected actually to get such a loud signal so soon in our run that we could pick it out by eye, essentially. Right? We spent all this time writing software, and really we should have just had grad students kind of look at the data, right? And these pictures up here are an artist's rendition of what happens. So they inspiral, they merge, and then they become spherically symmetric, and that's the ring down phase. It made a lot of news worldwide. This is just a sampling of some of the front page news covers from around the world that were talking about this detection. And I actually had a much nicer slide, a lot more professional, but it didn't have Ruth in the corner there. That's my daughter. She was a lion yesterday for Halloween. It was really cute. So I want to talk a little bit about the signal, and I pulled a graph from the first paper, which might be a little bit intimidating for people who don't have a scientific background, but I'm going to walk through every step, what convinced us that we found a gravitational wave and why we're so convinced. All right, so in the top left is the data from the Hanford, Washington site in red, with just slight modifications to the data, and you can see by eye that there's something different than the rest of the noise. Okay, and I've already described how it has a low frequency, then a high frequency, and the amplitude does exactly what we would expect for an inspiraling system. Now the top right has another signal in blue. That's the signal from the Livingston detector. And underneath it, so it too has the same properties, and then underneath it, we took the data in red, so from the Hanford site, and then we shifted the data to line up. And the shift that happened is because the gravitational wave will hit one detector, travel at the speed of light, hit the other detector. So there's some time that it takes for them to hit one detector and another, so there's a time shift that you have to apply in order to see them line up like this. And the reason we did this is so that you could see how well they agree. Right? The frequency evolution seems to be spot on. Okay, so that's convincing. Not only does it happen in one detector, which is odd enough, but it happened in two detectors within a light travel time of each other. Right? So that's a big coincidence there. The second series of plots show the numerical relativity simulations for this system. So we did all that parameter estimation. We took all of these guesses. But the models we use to make these guesses are actually approximates. They approximate general relativity, and they're not exact. The only way we can solve Einstein's equations in general relativity exactly or within machine precision is with computers. So we take those best guesses, those parameters for the best guesses, and we input those into our numerical relativity simulations, and weeks, maybe months later, we get a numerical relativity simulation which looks like this in red and blue, adjusted for how it would show up in each of the two detectors. And then, the third series of plots, we subtract the two. And you can see in red and blue that we just have normally distributed noise. We've subtracted out all of the signal. The signal matched exactly what we expected from general relativity. So there's the huge coincidence that they happen at the same time, or roughly the same time. They happen with essentially the right frequency evolution you can see by eye, and then that they match our theory so precisely, we're really sure that this is a gravitational wave. Okay, so let's describe the system a little bit. There are two masses orbiting. The first mass, the primary black hole, the bigger one, is 36 times the mass of the sun. The second one is about 29 times the mass of the sun, and the error, our uncertainty is in the right column there. I'm just going to quote the medians. And then when they merge, they form another black hole, which is 62 times the mass of the sun. And for anyone doing math in your head, you might realize that they don't add up. So what happened? Well, the system lost energy to gravitational waves, and through E equals mc squared, you can figure out how much mass that is equivalent to, and that's the mass loss through gravitational waves to get to the remnant. How far away was it? About 1.3 giga light years away. Giga means billion, so it took light, or gravitational waves traveling at the speed of light, 1.9 billion years to get here. So we're looking way in the past when we see these things. Unfortunately, the components that we suspect to be spinning, we couldn't find any spin, or we couldn't really measure the spin. Not that we couldn't find it, we couldn't constrain the spin. But the remnant spin is about 0.7-ish. And what does that mean? Well, there's a maximum amount in general relativity that a black hole can spin. We call that 1. And there's a minimum amount it can spin non-spinning. That's 0. So this is about 70% of the maximal possible spin. Okay, and here's a quick simulation of what's happening. So at the bottom here, you're tracking through the gravitational waveform. This is a numerical relativity simulation, so all of the general relativity is correct. The curvature here is the curving of space-time projected into 2 dimensions. And you can see as it slows down here, it doesn't actually slow down, but we've slowed down the video. You can see extreme curvature right before it merges. It's not completely spherically symmetric. Now it pretty much is. And then you can see the gravitational waves radiating away. So that's the system that we saw. To give you a size, it's roughly the size of Iceland. So we take all of those 60-plus mass of the suns and put them in an area that's roughly the size of Iceland. And that's the black hole, the remnant black hole that we saw. Okay, and then we saw another one. This one I call the Christmas present. It's called GW 2015, 12 December 26. But in the US, it was 10:30 on the 25th, so it's a Christmas present to everyone here. This one you couldn't quite see by eye. This is more along the lines of what we expected. It was a smaller mass system. It was a lot longer. The duration in band was longer. So what we did was we took the noise from the detectors, which is in the top left and the top right, and in black underneath, we showed you what the signal looked like, so that you can at least see the noise kind of seems to oscillate in lines along the same lines as the underlying plot there. So what was really important here is part 2 of my talk, the signal-to-noise ratio, because you can't really see the signal in the top 2 plots, but if you go down 1, 2 plots, you can see the y-axis is SNR, that's signal-to-noise ratio, that's the signal power statistic. You can see that there's a significant peak in both the Hanford and Washington signal-to-noise ratio statistic. So we found this with our match filter searches. The parameters here, the big black hole was 14 times the mass of the sun. The smaller one was about 7.5 times the mass of the sun. They combined to make a 21 times the mass of the sun black hole, about 1.4 gigalight years away, so roughly the same distance. But the component spins we were able to constrain a little bit better. The 14 solar mass one had a spin of about 20% of its maximum possible value. Okay, and here's a simulation of what this looks like. The gravitational waveform is on the bottom. These are much smaller signals, or much smaller black holes, as you can see here. And the curvature, again, is the curvature of space-time. The different colors just kind of help you see that a little bit better. And you can see the gravitational waves propagating in every direction as they inspiral. And eventually, they will collide, and you'll see the extreme gravitational waves propagate away and then completely die off. So this, again, is another numerical relativity simulation here. Cool. Okay. So what we saw in our runs was a confirmed event in September 14th. That was the big thing, the big black holes. And then we saw slightly smaller black holes December 26th. And what I haven't told you about was actually another candidate which didn't pass our threshold of what we would call a detection, but was still likely astrophysical. And I'm running a little bit low on time here, so I'm just going to tell us what we learned instead of going on more about that. So what we learned is that gravitational waves exist, right? We kind of knew that, but now we really know that. This is our first direct detection of gravitational waves. They seem consistent with general relativity, and they exist in binaries, right? We've actually never seen them in binaries like this. And then they merge and make even bigger ones. And in fact, we've revealed a new class of black holes that we had never seen before. We had seen stellar mass black holes, roughly 5 to 20 times the mass of the sun. We've seen supermassive black holes, like millions of times the mass of the sun. And we've actually opened up a new regime of black holes that we never knew existed. And that's where I'm gonna end the talk. So you can see the new regime of black holes that we've opened up, whereas those in the bottom left through the X-ray studies were what we had seen before. So thank you for having me.
The Origin Science Scholars Lectures are presented by Case Western Reserve University's Institute for the Science of Origins, with the assistance of the Siegel Lifelong Learning Program, the College of Arts and Sciences, and MediaVision. For more information on the Origin Science Scholars Program, including a full video archive, please visit the Institute's website at origins.case.edu.